until a certain point, and then we don't, and after that it's speculation. So there are no other better explanations yet, but I wouldn't be surprised if in your lifetime a few things will happen. Either we will look closer to the Big Bang and say that really happened, or we'll be able to look closer into, back in time and say, no, maybe it was something different. It could be either, but at the moment it's the best picture we have of the origin of the universe. I'll take one there, and I'll take up there, yeah. I repeat it.
So your work with gravitational waves had a lot to do with the general theory of relativity, and obviously quantum mechanics doesn't really reconcile with that. So I wanted to ask what work is currently being done towards a unified theory.
Yeah, so look, it's a very technical question. I'll put a little bit of explanation on it. We have a theory of gravity, that's general relativity, and we have a theory of the very microscopic world, which is quantum theory. And one of the big tensions in physics right now is that we don't know how to quantize gravity. So what happens to gravity as you get to smaller and smaller scales? And that's the question that's being asked. And there's this idea of having a unified theory, which means that at some point you should be able to describe gravity quantum mechanically. And there's a number of theoretical physics things going on, things like string theory, there are certain other quantum field theories. There has been no major breakthrough in that in the last 30 years. We've gotten better at doing the math, but I would say it remains one of the great puzzles of theoretical physics. So my experiment, by the way, will say very little about that, because we don't look at the quantization of gravity. Yeah. No, I want to hear from these guys here.
So now that you have all these new discoveries and you're making a great breakthrough in science, which congratulations, by the way.
You.
So what does that lead towards the future of the universe? How will that help us better understand what's happening around us?
Yeah, so that's a really nice question, and ties back very nicely to the question on the Big Bang here. So I'll give you one example. There are about 30 things I talk about. I'll tell you one. And I'll tell you the one that's the most exciting to me. Remember, I started this asking the question, where do we come from? So when you look at the Big Bang, what you see is that as the universe was expanding, when the universe was very young, it's very dense. Everything is packed into a small volume. And at that moment in time, light could not escape. So light, it turns out, there's a really nice story I'll tell you about light and gravitational waves. They're both waves, but they're a little bit different. So light is like going to a party. Say you go to a party, you go with a friend, and you say you're ready to leave. And your friend, oh my goodness, she has to say goodbye to everyone. She has to chat with everyone. An hour later, you get to leave the party. And light is like that. It meets atoms. It wants to interact. It scatters off of atoms. It diffracts. It refracts, all of that. Gravitational waves, on the other hand, are like your other friend. You say you want to leave the party, and they're not even polite enough to go say goodbye to the host. They're out the door, right? So they leave right away. And so they don't interact with matter. And as a result, if you want to look at the early universe, when light was trapped inside this hot, dense tube, the only way you can look at the very early universe is using gravitational waves. So now I'll give you the numbers. If you use light, the earliest moment in time, you can see the universe, when the universe got big enough that the light didn't meet atoms all the time, was when the universe was 400,000 years old. So if you want to learn about the Big Bang, light only takes you up to 400,000 years. Now, it's still pretty good given that the universe is 13.5 billion years old. That's still pretty young universe. But if you want to look any further back, so for example, if the LIGO experiment was about a factor of 10 to 100,000 more sensitive, so really tall order, it's not, the gravitational waves we would see from the Big Bang would be 10 to the minus 22 seconds after the Big Bang. So 400,000 years, 10 to the minus 22 seconds. All right? So in your lifetime, maybe we'll see that. In my lifetime, I think we'll just keep making progress towards that. And lots of things along the way. We've never seen supernovae. We'll see that. So I think there's lots of interesting things in the universe. But if you really want to know where you came from, gravity. So, sure.
So my question is related to black holes. So we know that supermassive black holes formation of, when gases collapse on each other. But I really need to understand how they actually die off through, there's something called Hawking radiation. I'm not entirely sure how that works, so it would be good if you could explain that.
All right. All right. My apologies to those of you who don't care about that, but it is actually pretty cool. So I'll tell you. So there's a kind of radiation that, so you've heard me say that black holes give off no light. And the answer is that's not quite true. If the black hole were if there were no such thing as quantum mechanics, then indeed the black hole would give off no light. But in quantum mechanics, what happens is the quantum mechanical description of a black hole results in something called Hawking radiation, named after Stephen Hawking. And what this really is it's kind of, I'm going to tell you a bunch of things that even if you don't follow them, they'll blow your mind. So the first thing I'm going to tell you is that in quantum mechanics, there is no such thing as empty space. So you've heard of space as a perfect vacuum. On average, it's a perfect vacuum, but what's in quantum mechanically, when you look at empty space, particles and their antiparticles, so electrons and anti-electrons, are constantly coming into existence and then dying in a poof of energy. Now this is going on all the time. So you think you're in this pristine, quiet, empty space all around you. Even here, we have particles and antiparticles coming into existence. And what happens at the edge of a black hole is the interesting thing. So imagine there's the edge of a black hole and a particle and an antiparticle came into existence. And the particle got sucked into the black hole by its gravity, but the antiparticle was just far enough away that it escaped. And now you've broken that particle-antiparticle symmetry. And that's what Hawking radiation is. So, and it should, in principle, be measurable, that the little flash of light should be given off every time a black hole does that. We have no hope of seeing that with current technology. But it's certainly mathematically and physically plausible. So for the rest of you, the amazing thing is particles and antiparticles, we are surrounded by a popcorn of them coming into existence, meeting each other, annihilating. So they create, they annihilate, and there's a popcorn of energy all around us. So two things you've learned today. Space-time can warp and ripple and tear, and space is not quiet or empty. All right. Do you have time for more?
Yeah, I thought I'd ask the question I was preparing for you.
Oh my goodness, you prepared a question.
I prepared a question. Oh, you have? Yes.
Yeah, there's a couple more too, but we'll take your question too.
Okay.
Why don't you use like moderator privilege and ask your
moderator privilege. My question was that if I was sitting in their space, I want to be like you. How do I become like you? And what roadmap can I take? What steps can I take at this age to reach where you are? Can you give them a blueprint?
Yes, listen to your parents, listen to your teachers. No, don't do that. Yeah, okay, look, that's a really a profound question. I don't think there is a single roadmap. Each of us takes a different path. What I can say is my own story, as you heard, was that I started off in my O-levels and my A-levels very much focused on math and science. And then I went to college with the idea that I had become too narrow already. So I went to a liberal arts college so I could then do math and science, which I wanted to do, but also do humanities and arts and social sciences, which I did. And so I would say for you all sitting here, wherever you go to college or university, if you're excited by discovery, try to get some kind of internship or research position early on. That was what sparked me, was getting away from problem sets and homework problems to working on problems that were actually interesting, relevant, important, and where I could make a difference, right? If you're just sitting in a classroom solving problems with 20 of your friends, it's good for you, but it's not changing the world. Right? So that would be the first thing to say, get involved in research as early as you can. And then comes the question of whether you want to, if you want to have a life in research, then it is necessary, certainly in physics and in almost every field that I know, to get a PhD. And I would say, I don't know very much as much in the Pakistani context, but in the US, in Europe, in the UK, most places, when you do a PhD, you actually get paid. So you get paid a stipend as a student. You can actually live a modest life. And so for those of us who are financially strapped, thinking about an education process that can take 10 years from